Alright, so this video we're going to be going over some of the source code, just giving pointers for the next group on what things do, what each folder is for, and what some of these bash scripts are. So first, we have a tutorials and documentation folder. So this will be very helpful. There's stuff about just installing everything that's necessary. Yeah, definitely, if you're the next group working on this, look through this folder, and this should be pretty helpful. And then we have a README, obviously. These bash scripts, so it's really just a few lines, but it's just meant to make it a little bit easier to start the programs. So this would be the command that you normally use to run the program after sourcing ROS Eloquent and then sourcing the workspace. So it'll just do 3 commands for you. So run manual control starts our program. Start bridge starts the ROS1 bridge and also ROS core, which you will need because this is all written in ROS2, and the edu the package for the edu source code is all in ROS1. So you'll need to run the bridge when you're using the real robot, and this will pass messages from our program in ROS2 to ROS1, and also vice versa, from ROS1 to ROS2. This package is the bridge. You can mostly find this online, but we've included this because we actually ended up making some modifications. So the main one is this mapping rule. So this specifically, you have to write mapping rules for messages from ROS1 to ROS2 that don't line up, so that the bridge can know what to pair. So for example, with this message, this is the name of one of the fields, command flag. This is ROS1, and ROS2 doesn't allow you to have capital letters, so we had to rename it to command underscore flag. So that's what this is. This is the general format. This is in the tutorials how to make this, but we've just included the whole ROS bridge package because we also had to modify CMakeList and the package XML, and it just, yeah, so you can just build this directly instead of having to get it from the other GitHub. What else in here? So we have actually modified this. I don't think you'll need to use it. At one point we thought that we would need this. This is basically just an executable that comes with the program, but then we modified it to work with joint state array because we were having some problems. You most likely won't need to use this, but it is an option. I think that's everything. Dynamic bridge is the CPP file that you'll be using most of the time though. Alright, so this ROS2 folder is really what has all of our original source code in it. So starting with edu core messages, this is just basically translating the message package that was originally in ROS1 into ROS2. They didn't have a ROS2 version online, so we just had to make the modifications ourselves. There's not really much to look over in this, but you can see in here, this is all the messages. If you click on one, it's basically just defining almost like a class or something. It's defining like a data type that ROS can use. This is the service file. We don't use any of these in our program, but we did translate them just because they're in the original edu core package, or edu core messages, so we just translated everything. This is, okay, so edu manual control is really the main thing that we were working on all semester. So I'll show you the CMake list in package XML because that might be a little bit helpful. So generally, the format for a CMake list.txt file, this is used basically to tell the computer how to build the program. So there's commands like this, find package. You need to list any packages that are outside of like that we're using but we didn't write, or packages that we did write but still need to use. You do find package and then the name. So this is you can add like libraries to all these files. Basically get, like, next time you use this, like basically this class CPP files references these four files. So then you can read through this target compile definitions. Most of this is really just like you can find templates for this from the ROS tutorials, and then you just have to add in like fill in the blanks basically to make it work for your programs. Anytime you want to have an executable, like if you want to be able to use your program in the command line, you use this command, you give it a name, and then you say what file the executable correlates to. And then target link libraries. The format for this is basically just like what libraries will that executable need. So we say sample CLI, which is what we just defined up here, and then curses library. That is for ncurses, which it's used in the jog function for basically like manipulating the terminal display to like erase it, and then also take multiple inputs per key press. This is the CPP files we were just talking about. And then for ament target dependencies, I'm actually not even sure what exactly the difference between these two is, but I think this is you include other packages. So the format is, this first one is the executable, and then RCL-CPP, that's the main library for ROS2. Standard messages, that's just like all this like ROS2 standard messages, and then edu core messages. And so that means that this executable relies on these three other ROS packages. And then install executable, and then this gives you the destination. So for the package XML, this is the general format. You give it a name. I don't even think the version number really matters. None of this stuff is necessary, I don't think. I'm up here, except for the name. And then you say what build tool to use. So basically any ROS2 package is built with ament CMake or Colcon. I think Colcon uses ament. I think that's how it works. And then you declare dependencies. So these are other packages: RCL-CPP, standard messages, edu core messages, curses. And then the rest of this stuff is just from a template. Yeah, the rest of this stuff is just from a template. I don't even specifically know what ament lint auto is, but if you look up the ROS tutorials, they all have these included. Alright, so for the source code, let's start with sample CLI. So sample command line interface, this is the executable we were seeing earlier. So I'm not going to go too in detail about everything, but just generally, this up here, RCL, CPP, and NIT, you have to do this for every ROS2 program at the start. And then this is declaring nodes. So our program is actually, even though it's one executable, it's I think 4 different nodes. Yeah, I think it has 4 different nodes in it. Just for different functions, so that like jog is separated from move, and calibration is also a separate node. Executors are pretty helpful if you look up the documentation on them. Basically just lets you do some extra things with nodes that like a standard node doesn't let you do. So we use these in some parts of the code, and other parts we don't need it, so we don't use it. These are instructions for testing. Yeah, you can. This is just kind of for whoever is working on it. Like if you want to run it from home when you're not with the robot, follow these instructions, and it should make it a bit easier. And here is the command line interface. So this is what the user will see. Press 1 for jog control, 2 for move control, 3 for recalibrate, 4 to print the data. And then just a switch case calls different functions based on what choice you chose. So all of these functions are stored in this file for the most part. I guess not all of them, but for the most part this is our main file that we are writing code in. There's some other, I think there's 3 or 4 other classes that also have functions that are used in edo functions. So let's start with the classes. So for data display, this basically just creates subscribers and then prints data. So for example, Cartesian pose sub, Cartesian pose subscriber. What this code means, you say this, so it's referring to this object, and this is the constructor, by the way. So this object, and this object inherits RCL CPP node, and this is the node name, data display. So yes, data display, create subscription, that is a function from RCL CPP. Data type, edo core messages, message, Cartesian pose, basically saying this is the type of message that you're going to receive, and then the topic. So there's, on the other end with the robot, there is a publisher publishing this same data type to this topic, and that's kind of how that works. 10, this is like this is an argument that we don't really understand. It's like the quality of service argument. I've looked up what it does, but for the most part everything is just 10, so we haven't really had to mess with that at all. And then this argument right here is saying this is when you receive a message, pass that data or that message to this function. So data display print pose data. So basically, yeah, whenever this subscriber gets a message, this function will get called, and that message that it received will be passed as a parameter. And then, so for this, this basically just means we don't want to print it twice. So if Cartesian printed is true, it will not print anything. And if it's false, then meaning this is the first time that a message has been received, it'll print all the data in the message, and then set Cartesian printed to true. Now, basically the rest of the functions are the same thing. So there's 3 subscribers. They all have very similar functions. And then all of these booleans start off as false. There are also these boolean functions that just return if Cartesian printed. It just returns if that boolean, the value of that boolean, that's all it does. And we use it in edo functions quite a bit. So I'm not going to go over the other functions because they're all really similar. Yeah, what I just said about this is also true for these. It's just different topics and different data types, and then it passes them to different functions. Alright, movement command queue. This is the one that confuses me the most. I didn't work on it, but I'll try to explain it still. So this is similar to data display. It's a class that inherits RCL-CPP node. So basically you're just extending some of the functionality of the standard node. So same thing I just showed you. This is a subscriber. I'm not going to go over that because I just went over it in a different thing. But this one is a publisher, and we have not seen this yet. So move control pub, this create publisher, and then this is now saying we're going to send out this type of data, and we're going to publish it to bridge move, that's the topic, and then this is quality of service. Again, we don't know what that does. This, I did not write this code. I'm honestly not sure what this is for, but maybe we'll see lower down. So the difference between these, when you initialize a subscriber, it just starts listening. When you initialize a publisher, it doesn't publish anything until you tell it to publish something. So here, send move command, you see this is the function that we just initialized in the constructor, and this is, we're using it here. You can use this by just passing a movement command message to this function, and then it publishes it. Move control pub, publish, and then the message. So this is where this file starts getting a little bit more complicated, and some of the parts that probably Adam understands better than I do. But so I believe at the top, or maybe it's, I believe this data type is defined in a different file, and I'll show you that later. But yeah, basically there's 3 queues: waiting executed queue, waiting received queue, and waiting pending queue, right, or pending queue. So this is push move command. So with these 3 queues, basically it needs to check. What's basically going to happen with this is when you push a movement command, you have the option to say you want to push like 10 movement commands all in a certain order. So movement commands are along the lines of move joint 1 to like degree 10, and then you could give another command that says move joint 2 to degree 15 and joint 3 to 180, or something like that. So when you input multiple commands at once, they can't just all get sent at once. So there's this queue system, and this makes sure that movement commands are not pushed until the other movement command has been received and executed. So waiting received queue, I believe that means the robot is also constantly sending back feedback. Like when you send in a move command, it'll send back, okay, I received this, and then it'll also send a message when it is done executing. So yeah, I'm a little fuzzy on the exact implementation of this, but I know that yeah, there's basically three states, like the message has been sent and received, or it hasn't been sent yet, or it's been sent, received, and executed. So that's kind of what this is. This code is doing, is just tracking all that. So what I was saying about the edo is constantly sending back feedback. That's what the subscriber is listening for. So movement feedback, machine movement acknowledge is the topic. So this is like when we send a movement command, this subscriber listens for the edo's response so that we can know when to send the next movement command. So this movement feedback data type is used right here, and the movement feedback data type has a field within it called type, and that'll just be a number from like 0, 1, or 2. And so that says like the robot's sending back feedback, and 0 means the command was received, 1 means I think 1 means I'm actually not sure, and then 2 means the command has been executed. I think it means that the machine is ready to receive another message, but it has not executed yet, but it's ready to receive another message. And so this is all handling the queues, moving messages from one queue to another, or popping and pushing. So that's what all this is doing. So this, like I said, you can do you could do like 10 commands at once, 10 movement commands at once, and the edo will execute them in the order that you input them. And so this command, or this function, is just, we'll use this in a different file to make sure that the program doesn't move on until all the queues are empty, which means that all the commands have been executed and there's no more commands waiting. So that's what this is used for. State checker is pretty straightforward. The machine can have a few states. It can be in state calibrate, not calibrate, movement, I think break are the 4 that we use in our program. So this is same thing. It is a class that inherits from node, creates a subscription to machine state, and then we use it in our program to make sure, like to see, has the robot been calibrated, does it need to be calibrated, is a different program currently moving it, in which case we shouldn't also try to move it, that kind of stuff. So state checker, state callback, this is again the function. This parameter is the function that will get called whenever the subscriber receives a message. So here it just prints that out, and then it sets state received to true, so that we know Like, we don't need to keep on receiving the machine state once we've received it once. And then it sets the machine state to this variable. I believe this is just an integer, maybe an unsigned integer. This is just a getter. This is also a getter per the Boolean. So I think the only one that's left is edo functions. So this one is quite a bit bigger than the other files. This is really where we use all the classes, and this is where all those functions that were used in the command line interface are located. So we might as well take a second to look at the include statement so you know what's important. This is ROS2. Anytime you're writing anything in ROS2, you include RCL CPP. These are the classes that we just went over, and these are data types. So you saw earlier in the CMake list that edo core messages is a required package. So this is why we need to tell the program when it's building to basically include these messages, include the whole package really. So this is the format. It's kind of weird because if you look at the messages, these are actually, they don't have an underscore between them. It's like capital M, capital C, but just when you compile a message package, it like auto-generates these files, and the names get changed to all lowercase with underscores. These are all pretty much normal. And then ncurses, I talked about that a little bit earlier, but I'll show you in the jog function when we get to it what that's used for. So let's skip this one for now. Skip this one too. And let's go to jog, because those functions that I just skipped over are all used in jog, so they wouldn't really make sense until you see this function. So I'm going to try going a little bit faster because we're almost at 30 minutes. So this data type is this is how fast, it's just something in ROS, it's like basically just an amount of time. This is creating the publisher for the jog command. This is using the create jog function up there. All that the create jog function does is it just fills in the the fields of the movement command data type and then returns it. And so that just is kind of an ease of use thing. This is the command line interface, and this is where ncurses is used. And all this stuff just essentially makes it look nice, but also this right here is basically when in this function, if you're holding down the Q key instead of one button press, it'll count as, it'll count as many for as long as you hold it. So then, depending on what button you press, it controls a different joint in real time. U and J control the velocity, and then IK controls the gripper, which is like a little hand thing. So it's like a jog helper real quick. This is what actually publishes the data type. This is an obnoxiously long data type, but it was kind of unavoidable. But that's why this looks so ugly, because it's just this data type goes from here to here. Because it's like edo core message, movement command, fc allocator void. It's just a lot. So here, publish the message, sleep for a little bit. This is the message to be published, the joint number to publish to, the publisher, the loop rate I was talking about, and then the velocity. Moving on. And calibrate function. This also uses jog. You create a publisher. Also, this is really useful because of you saw how long some of the data types can be. Using auto is really nice. Create a publisher, set the loop rate, declare a joint calibration message, set a time span. This whole block of code, where does it end? I think it ends there. This whole block of code is if the robot has not been calibrated. So if the robot has been calibrated already, this recalib boolean should be false. Yeah, it should be false. Meaning you can skip all these steps if you've already calibrated once, because this is stuff that is sending a reset message, an initialization message, undoing, like releasing the brakes. So this you'll see, I think, 3 times, while reset pub get subscription count equals 0. So basically it's saying don't move on with the program until something is listening, and then you can publish. Because if you publish and nothing is listening, then the robot's not going to receive it. So that's what that's about. And then here we call the jog function, and then the user has to manually move each joint. There's like a little mark on the robot. The user moves each joint to that mark using the jog function. And then you set this value. This is like the value that tells the robot. 63 basically means calibrated. Like set these as, set the current state of the machine to be 0. Like tell the machine where your joint's at right now is the base, like the core, like standard to base everything off of. Same thing here, get subscription count. Once there's a subscriber, then you publish. So get data, this uses data display. So here, this is kind of similar to when we were declaring the other publishers, but this time we're declaring the data type is data display, which inherits from the RCL CPP node. So this data display, once you initialize it, you can add it to the executor and then say while RCL CPP OK, and these are all the functions that I was showing you earlier. Basically, this will keep on spinning until all of the data, like each of those subscribers in data display, has received and printed a message. And then you always have to remove nodes from the executor once you're done using them. So the reason we use executor is because spin sum is really useful, and that is allowed by executors. And basically it's, I'm not sure if at this point you know what spinning is, but when you spin a node, it basically starts running, checking for data. And when you do spin once, it'll check one time. When you do spin sum, it will check it'll check until it receives something, and then once it receives something, then I'm pretty sure that's how it works at least. It's similar to spin once though. They can sometimes be used interchangeably. initial startup. So this is where state checker is used, same thing as above with data display. You declare that variable that is of type state checker, and then you add it to the executor. While state checker until you receive that message, keep on spinning. It'll keep on printing check machine state, and then you remove it. You remove the node from the executor. Now, depending on what the state was, so like I said, it can either be calibrate, not calibrate. Oh, init, I forgot. Move, and then machine. Oh, I guess there's more than I mentioned. Machine error, braked, command state. So it just does different things based on what the machine state is. So for example, 0 or 1, if the machine has not been initialized or if it hasn't been calibrated, you have to calibrate it. So that's what that does. If it's already been calibrated, don't do anything, just leave the function. If it's being moved, it shouldn't be being moved, because that means that some other program currently has control over it. Same with jog. So these will basically, like, it'll say fetch new state. It won't let you do anything until the state isn't move or jog. And you get the point. Move. This is what I was talking about earlier, where you can send multiple commands at once and tell the machine do these commands in this order. So this is like the one part of our code that isn't fully working. So joint movement to joint point works, but anything involving Cartesian is not working, and is also not working with the tablet, like their tablet app. It's not working on the eDo, and it's not working on the ROS1 version of this program. So kind of hit a wall. We didn't, and then COVID hit, and so these three, if you try them out on the real robot, will not work. So this is just doing some prompting from the user, and then let's just, for the one, I'll just go over the one that works. This is what it'll look like. So you enter, as the user, you would enter like 0, 0, 10, 10, 15, whatever degree you want each joint to move to. And if you say 5 entries, you do that 5 times. If you say 1 entry, you do that 1 time. So this is kind of similar to the create jog. It's just initializing a variable of type movement command. And just there's a lot of values, so it's just nice to have that in a separate function. So you can just call this and then initialize a variable with it. It does have some logic compared to create jog, but it's the same function, same idea. So this, you enter the times, like, so if you, loops is different from the amount of entries, because you could enter 2 commands, like say move joint 1 to position 20, and then the second command would be move it to position 0. But you could say, but loop that 10 times, and then it'll just go back and forth 10 times. I did not write this function, I don't know. This is using that movement command Q class, and then here you keep on spinning until that still running function returns false, and then you can be done. So I think that's everything. I didn't think this would take 40 minutes, but I guess going over all the code does take quite a bit. I hope this was helpful, and good luck.